we have another characterization of connectedness in a topological space. Connectedness in a topological space. So what are we saying in that case? We are letting T to be a topological space. So T is connected. Observe that T is connected if and only if for every subset H of T such that that subset is not empty and that subset is not T itself, the boundary is non-empty. So the statement is, this is another characterization of connectedness. What conditions do we know? We know that T is connected if it has no separation. T is connected if and only if what? If and only if the only Kloppeny subsets of T closed and open subsets of T are T and the empty set itself. That is also a characterization of connectedness. Now we are saying that a topological space T is connected if and only if for every non-empty not equal to T subset of T, the boundary of that set is non-empty. So we are going to prove the forward direction. Forward direction. So we are going to suppose that T is connected. Then we want to show that the boundary is non-empty. We are going to prove this by contrapositive. So we are going to show that T not connected should imply that boundary of H is empty. T not connected should imply that the boundary of H is empty. So suppose that T is not connected. This implies that we define connectedness in the preliminaries. In the preliminary video, we say that a topological space is connected if and only if its closed and open subsets are the empty set and that set X itself. So if we are saying that it's not connected, this implies that there exists H, a subset of T, such that H is Kloppeny. H closed implies that H closure is equal to H. H open implies that T minus H is closed. T minus H is closed, i.e. T minus H closure is equal to T minus H. So we want to show that the boundary of H is empty. So by definition, the boundary of H is equal to H closure intersection T minus H closure. H closure is equal to H intersection T minus H closure. This is T minus H. So T intersection its complement. This is actually an empty set. So this implies that the boundary of H is empty. So T not connected implies that the boundary is empty. So this implies that T connected should imply that boundary of H is non-empty via contrapositive argument. So that is the forward direction. Now the backward direction, conversely, what we are going to suppose that I think this one should also follow contrapositive argument. Suppose that conversely we want to show that boundary of H empty should imply that T is connected. Should imply that T is connected. So suppose that boundary of H empty should imply that T not, sorry, now contrapositive. Boundary of H empty should imply that T is not connected. Now, I think at one point in time I proved something. I proved that the boundary is empty if the boundary of any set is empty if and only if that set is open. We prove that statement. So if the boundary is empty, that means that set is closed and open. I prove that statement. Kindly look through those videos. So the boundary of H being an empty set, this implies that H is closed and open. H is closed and open, so this implies that empty set H and T are open. Now, for a set to be connected, the only open subsets of that set are supposed to be T and the empty set. Now we are including H. This implies that T is not connected. Hence, we are done via contrapositive arguments.